Okay, so we're going to be talking about the Pearson chi-square test today and discuss relative risk and odds ratios, as well as alternatives to chi-square. So if at any point you have any questions, just raise your hand and we can discuss any points further. All right, so what I would like to start with is to say that categorical data is very prevalent in public health. And typically, we start analysis of categorical data by looking at what we call bivariate associations, which essentially means that we are looking at an association between two categorical variables. And I'm sure you guys have seen categorical data many times. Anytime you see a contingency table, that's what we are talking about. So we are going to discuss the analysis of such data using an example. And then we're going to go over hypothesis testing steps, and then finally talk about the strength of the association. So first, we're going to look at very well-known data. This data, well, the question that generated this data set had to do with looking at the association between race of the defendant and death penalty verdict. Right? You can probably imagine that this was a very hard question. And if you have a hypothesis, there is a discrimination, then you can either find, well, let me just rephrase that. If you're interested in either refuting a hypothesis or finding evidence for a hypothesis, one way to do that is to collect data, right? So in this particular case, we are looking at the classification of all court trials concerning homicides. And this data comes from Florida between 1976 and 1987. And you can see that on the left-hand side, you have race of the defendant. In our case, we have white and black categories. And then across the top, you have the death penalty verdict. So we have obviously yes or no, right? So if you look at this data set, we can see that we have over 10,000 cases. If you look at the marginals, you can also see that you have 364 death penalties. And in terms of the distribution of the race, we can see that you have about 5,000 white defendants and 5,000 black defendants. All right, so first question, does there exist evidence of discrimination in the death penalty verdict? And probabilistically, you can ask the same question by asking, is death penalty verdict independent of race of the defendant? So just by looking at those numbers, what would be your conclusion? Can you tell? So I think the fact that you are not giving me the answer sort of tells us that looking at the count data typically doesn't give you a clue about the association. So we should be looking at conditional probabilities, right? So one way to do that would be to say, what percentage of white defendants got death penalty versus what percentage of black defendants got death penalty? Would you guys agree that this is the way to approach the problem? Sure. Okay, so let's just set a test of hypotheses so we can formally test the hypothesis of interest here. So as in all hypothesis testing procedures, we first assume that there is no association between the variables of interest, right? So that's the null. There's no effect, there's no association. So in our case, we will have to say that under null hypothesis, death penalty verdict is independent of race. And in the alternative hypothesis, we will say death penalty verdict and race are not independent. In other words, they are associated. Okay, and then we can write this hypothesis also using probability statements. So the probability of getting death penalty among whites is the same as the probability of getting the death penalty among blacks would be our null hypothesis. So note the equal sign in the null hypothesis. And then alternative hypothesis would specify the probability of getting death penalty among whites is not the same as the probability of getting death penalty among blacks. So writing hypothesis for the chi-square test is very similar to writing hypothesis for any other test that you guys covered already. The only difference I would say is that we tend to talk about independence in the null hypothesis and then in alternative hypothesis versus, let's say, equality of means or proportions. So the problem that we have at hand could be solved using the proportion test. So we call it here the proportion approach. And we already specified how we would do that. If the proportion of white defendants who get death penalty is similar to the proportion of black defendants who get death penalty, then you will have independence, right? And you can test it by saying that null hypothesis is that those proportions are equal. Alternative is that they're not equal. And then you will just use the two-sample z-test or confidence interval approach, which I believe you covered either a week or 2 weeks ago. Okay, but most commonly when we have when we display data in a contingency table, we actually use the contingency or frequency table approach, and that's what we're going to cover today. So the question then would be, what should you expect in terms of counts if there was no association between the variables of interest? And let me ask you a leading question to that. Let's say we are interested in looking at the ER visits over 1 week period. And we found out that there were 49 visits in that particular week to the ER. Now, if you thought that the day of the week is not associated with the number of visits to the ER, how many visits per day should there be approximately? 7, right? So if you saw that distribution 7 days, approximately 7 days in each of the days, then you will say the day does not matter. On the other hand, if you saw that there were many more visits around the weekend, then I think we would be all inclined to say that there is an association between the day of the week and number of visits. So the same idea applies here. If in fact that the verdict was independent of the race, then we should see a similar distribution of counts in our contingency table. All right, and then again, if those counts, what we call expected counts, differ from the observed counts, then we will have evidence of to reject the null hypothesis. So how do we do that? We can compute the expected counts under the null hypothesis. So remember, null hypothesis says that there is no association. In other words, there's independence. So we can, for the first cell, we can compute that count by knowing that the probability of white and death penalty is equal to the product of probability of white and probability of death penalty, of yes. Probability is a ratio of success to the total. So we can write it out as in the second row. And then if we want to look at the number of white and yes, so the count, the expected count in the first cell, we can just do simple arithmetic, and it will turn out that this is a product of the marginal for the row, the marginal for the column, over the total count in the table. So let's see how this works out here. If we are interested in getting the expected counts in the first cell, we're going to look at the row total for white. So we have 4,909 times row total, column total for yes, which is 364. So we multiply those two numbers and then divide it by the grand total. And this is how we computed the expected counts in the first cell. So we could go on and compute those counts the same way for each cell, but it turns out that in the 2x2 table, and actually for any R by C table, if we have fixed totals in those tables, we can easily compute expected counts if we know only a small number of counts. So for the 2x2 table, we only need to know the one count that we just computed. In the 2x3 table, we just need two upper left corner counts. And in the 3x3 table, we just need 4 upper left corner counts. So how does that work? Well, in here, you can see that to calculate the second cell in the first row, that is the red calculation in red, then we can take the total marginal, so 4,909, and then subtract the count that we already computed. And this way you get the expected count for that cell. So you're using very simple arithmetics to get those counts. Do you guys have any questions about that? Okay, so now we have the expected counts under the null hypothesis. We also have observed counts. And now there's a question about the difference. Are they very different or are they not so different, right? So in order to quantify those differences, we compute what we call chi-square test or chi-square test statistic. And it's denoted by chi-square. And then you can see that in the formula, we are summing the differences between observed and expected. And we actually square those differences first. So we work with positive numbers only. And then we also standardize that by the expected count. So again, the idea is to assess the size of the difference between observed and expected. And this is just a little bit of a maybe more fancy way to do that. So also for the 2x2 table, oftentimes we apply what's called the Yates correction. So it's a small modification to the formula that we had before. In here, we are looking at the absolute value in terms of the differences, and then just subtract a half. So this is a detail, okay? And it is also known that under the null hypothesis of independence, this chi-square statistic follows a chi-square distribution, and there are with the specified degrees of freedom. And those degrees of freedom for this test are R-1 times C-1, which basically means we will take the number of rows, subtract 1, we'll take number of columns, subtract 1, and then multiply those two numbers. So in your basic 2x2 table, how many degrees of freedom will you have? How many rows did we have, guys? 2 rows, so 2 minus 1 is 1. How many columns? 2 minus 1 is 1, so 1 degree of freedom. Okay, so now the question is our chi-square statistic that we computed just a second ago large enough to reject the null hypothesis, or is it not? So how can we judge that? Well, as before, you guys use the z-table, you use t-table. This time we're going to be using a chi-square table. So chi-square table on the left-hand side has degrees of freedom, which we just computed for our 2x2 table. And then across the top, it has upper tail area. So if we specified our test to be at alpha of 0.05, then we need to find that criterion to judge significance of our test. So can you tell me what is the critical value for 1 degree of freedom at alpha of 0.05 from your table? 3.84, right? So this is a critical value that is very good to remember, because oftentimes we work with those 2x2 tables. And if you remember that the critical value is 3.84, then you never have to go back to the table. You can easily know whether you reject null hypothesis or not. The question.
That's a silly question. How'd you get those numbers look small?
So they look small in here as well. So to find a critical value from this table, you first find the degrees of freedom. And that's, in our case, for the 2x2 table, it's 1. And then across the top, let's see. Let me just have a look here. I cannot see it either. I think the fourth column from the left is the alpha of 0.05.
Yeah.
Right. So if you look at the fourth column, you should see 3.84 as a critical value. Right. Okay. And also note that before, when you were using a z table or a t table, you were typically looking into both tails, right? So your alternative hypothesis was typically two-sided. In here, it is also two-sided. However, because we are working with differences and we square them, we only look into the right tail of the chi distribution. Okay, so it's a little bit different to what you guys known before. The same idea, a little bit different distribution, and one tail only. Any other questions, guys?
Question.
Sure.
I'm not quite sure I got what you just said. Does that, if we wanted to know if it's bigger or smaller, right? You know, like if, so we're talking about a different, or we're just looking at independence, it doesn't matter if it's a, if for example, that difference is less death penalties or more death penalties, is that going to show it or not?
So typically, when you look at this 2x2 table, you're interested to see whether expected counts are different from observed. That's the first thing. And second, sometimes expected counts are larger than observed, and sometimes they're smaller than observed. So in order not to work with negative numbers, we square that difference. So that gives you always a positive number for a difference. You can think about this perhaps in terms of absolute value. It's about the distance. The sign does not matter. If the distance is large, then your chi-square test will also be large. And if it's larger than 3.85 for the 2x2 table, then you will reject the null hypothesis and conclude that there's an association between the two variables. Any other questions, guys? Okay. So I just described that, so let me move on. Now, as every single test that we do in statistics has assumptions, so does Pearson chi-square, right? So the idea is that the test will perform well if the assumptions are fulfilled. Also, some of these assumptions are what we call robust. So moderate, hold on 1 second. Again, I have a problem here. I think it's crops. Okay. So sometimes when you have moderate violations of those assumptions, the results of the test will still be valid. But it's always worth looking at those assumptions to make sure that the test can be performed. So what are these assumptions for the Pearson chi-square? The first one is that each observation is independent. Did you guys talk about paired t-test already? Yes. Did you talk about independent t-test already? I think you did. So, Tony?
Single sample.
Single sample only?
Single sample.
Okay, so maybe that's why not quite yet. So observations has to be independent. In other words, if you have observations on the same subject collected over time, this test is not appropriate. Sample is representative of the population. So this idea is that it has to do with the fact that you either have a random sample taken from the population, or this data comes from an experimental study. Next, we have large sample size. So what does that mean in the context of categorical data? Well, it means that no cell in the table should have the expected count less than 1, and no more than 20% of cells should have expected counts less than 5. And this is important because we want to be able to use the central limit theorem that underlies those procedures. Okay, so sometimes, especially if you're testing means, your assumption will have to do with the total sample size. You will say you need a total sample size of 30 or more. And here, you have to look at the expected counts. Okay, and then there is a special test for small samples. It's called a binomial test. We are not really covering that in this class, but just know that if you're working with extremely small sample, then there is an alternative to the chi-square test. And what is also very nice here, though, is that this test does not have any assumptions about the population distribution. So in the t-test, for example, you know that the distribution, the underlying distribution has to be normal. And here, no such assumption is needed. Okay, so let's look at calculations and results. Actually, all right. So in the first part of the table, we have our observed counts. So that's what we have seen in our first slide. In the second part of the results here on the table, we have the expected counts, and this is what we just computed. Okay, so you can very easily compute a chi-square statistic looking or using Excel and using the formula we just had. In our case, the chi-square statistic is 39.07. So even if you did not have the p-value associated with that, you could already tell that we will reject the null hypothesis, right? Because this observed chi-square statistic value is greater than 3.84. But also, we can compute the p-value. So this is the area in the tail to the right of the chi-square statistic, and it's extremely small, 0.000004. Right, so therefore, the null hypothesis of independence is rejected. But now we should be looking at the direction of the association. In other words, we should look at the conditional percentages or proportions. So note that the proportion of death penalty verdicts among white defendants is 236 out of 4,909, which is 4.8%. And if you look at the same statistic, but for the black defendants, it is 128 out of 5,159, which is 2.5%. So what is the conclusion here?
More white defendants are have the death penalty.
Have the death penalty. So white defendants are more likely to receive death penalty. But now wait a minute. Do you think that when people started looking at this problem, that was their hypothesis? It's probably the other way around. Right? So we're going to come back to this, but can you think about a reason why we see what we see right now? Can there be a third variable, another factor that we don't see in the data we had right now that can explain that association? Go ahead. That's there could potentially be something there. In our data, though, we had about the same percentage of whites and black, or white and black defendants, right? So go ahead. Let's try.
The type of crime.
Type of crime could be a reason. Anything else?
Where.
Where? Okay, you guys are thinking about anything. Great.
Which state allows.
Which state allows the penalty? That's we are looking at the Florida case only. Very good.
Race of the victim.
Race of the victim. I think we have the winner. So we will look at that. We will look at that in a second at the data, which also incorporates the race of the victim, and you will see a very interesting result there. But before we get there, let's talk about statistics that allow us to quantify the strength of the association. So typically what happens when you do a chi-square analysis, you first run the test we just described, and then we will compute either odds ratio or relative risk, depending on the study that we are looking at. So let's look at both relative risk and odds ratio. So first, risk is the probability of a given outcome. In our case, this was the conditional probability of outcome based on the race of the defendant. Relative risk is actually a ratio of risks. So if you look at the definition, in the numerator we have probability of receiving death penalty given that the race was white, over the probability of receiving the death penalty given that the race was black. So you can see that this is a ratio of two probabilities. And if you compute those probabilities, you will get a relative risk of 1.94. How do we interpret that? So, well, let me ask a question differently. If there was no association between the variables of interest to us, this relative risk should have a value of 0, 1, right? If the probability of death penalty was the same for white defendants and black defendants, the ratio would be 1. Now, it is far from 1, right? It's actually about 2. So we can say that the probability of death penalty is twice as high in the first category versus the second category. So among whites versus among blacks. Okay, what about odds and odds ratio? Well, first, the definition of odds. Odds in favor of a specified event are P over 1 minus P, where the event occurs with probability P, right? So this is your typical definition of odds. So it's basically number of successes to number of failures. Odds ratio, again, would be a ratio of odds. So let's just look at this definition. In the numerator, you have probability of death penalty given the defendant is white over 1 minus probability of death penalty given the defendant is white. In the denominator, you will have the same, but now for blacks. So it is very easy to actually compute it. And if you did so, the odds ratio comes to 1.98. How do we interpret that? Well, we can say that the odds of receiving death penalty are almost twice as high among whites as compared to blacks. So if you guys paid attention to the interpretation of those statistics, you probably noticed that it matters which category is in the numerator, right? So if we're comparing whites to blacks, the category white should be placed in the numerator and black in the denominator. If you wanted to compare blacks to whites, you will just switch the order. Okay. And I would like to also mention that There's another way to compute the odds ratio. In other words, there are two ways to compute odds ratios. In terms of the computation, you notice probably that we're using conditional probabilities, right? And conditional probabilities sometimes can be computed, sometimes cannot. What's nice about odds ratio is that it can be computed from probability that we know exposure, and also from the probability that we know the disease, which matters in different study designs. So let me give you an example. If you are interested in computing odds ratio of lung cancer for smokers versus non-smokers, how can you think about this, designing the study or using data from studies that have already taken place? In a prospective context, you could start today, have your cohort, and record smoking status, and then look into the future to see whether the patient or participant develop a lung cancer. Do you guys agree that this is one of the ways to do it? Follow a cohort prospectively. In this case, you know the exposure, right? And then you will know the outcome. So you know the probability of disease given exposure. On the other hand, if you use retrospective studies, for example, case control studies, how does the data look like? Well, it's still a 2-by-2 table, but you typically know the disease because patients come into the hospital with lung cancer, and then you inquire about the exposure. Did you smoke? Okay, so what's nice about odds ratio is that you can compute it in both scenarios. When it comes to relative risk, you can compute it only in prospective studies. And this is one of the reasons why people use odds ratio more often than relative risk. Relative risk is easier to interpret, but it's not always possible to compute. Do you guys have any questions about this? Any comments? How many of you actually heard about odds ratios before? How about relative risk? Okay. Fewer people.
Actually, one more time, explain the difference between relative risk and odds ratio, the difference.
Okay, so the question is, what's the difference between relative risk and odds ratio? Relative risk compares probabilities. Okay, so you interpret that in terms of probabilities. Odds ratio compares odds, and therefore you interpret that in terms of odds. So it is easier to think about probabilities. We understand probabilities really well. It is typically not so easy to think about odds, but it is just easier to compute. So the difference is in the definition of the ratio.
Are they often very different from one another? Like in this case, they're pretty much the same, but does it ever happen that they are?
Sure. So the question is whether the relative risk and odds ratios are typically the same or not. So for rare events, they're typically almost the same. And you can think about this in terms of lottery. So let's see, if risk of winning is 1 over a million, then odds of winning are 1 to 999,999. Very similar, right? So these are rare events. And for common events, they're much more different. So an example here, if you're rolling a dice, the risk of getting a 1 is 1 out of 6. And the odds of getting a 1 is 1 in 5. Right? So those numbers will be different. Does this answer your question more or less? Okay.
Yeah, thank you.
Any other comments or questions, guys? All right, and I think we should look at the audience in online to see what questions they have.
There's a question about the Yates correction.
So there's a question about Yates correction, and the question was
When do you apply it?
when you apply it, when you use it. So the short answer to this is just it is recommended to use it in 2x2 table in general, because well, I don't want to go into the details of the technical details of that. Let's see what else we have. Oh, Tony, you answered. Thank you very much. Any other questions? Oh, okay, thank you. I thought there were more questions. It's just you
It's just chatter.
answering the other question. Okay, great. Okay, so moving on, let's just look at the distribution of death penalty verdict now by victim's race. So you can see that in our table now, on the left-hand side, we also included victim's race. In other words, we stratified our data by that third variable. So you can see that when the victim was white, we had about 5,076 cases. And in the second strata, when the victim's race was, I'm sorry, let's see what's going on here. Let me take it back. This is data for white victim race only. I was just ahead of myself. So let's look at this. We had 5,376 cases when the victim's race was white. In the top part of the table, we have the actual counts, so the observed counts. In the bottom part of the table, we computed the expected counts. So we repeated the analysis that we did before, but now stratified by victim's race. And you can see that the chi-square test in here, the value of the statistics is 67.06. So we reject the null hypothesis about the independence of race and receiving death penalty among cases in which the victim was white. There's an association. And now, since we know how to compute odds ratio, we could easily do that. So if we apply the formula that we discussed before, you will get an odds ratio of 0.42. Okay, so let's just think for a second. Odds ratio of 0.42, what does that mean? Who is more likely to get death penalty, white defendants or black defendants? Black defendants. So odds ratio of 1 would suggest that there's no association between the variables. Odds ratio that is greater than 1 will say that the odds of the outcome are higher for the white defendants. On the other hand, odds ratio less than 1 indicate that the odds of the outcome are higher for black defendants. So you have to always think about odds ratio in terms of whether it's 1 or larger than 1 or less than 1, and then interpret that correctly. Let's move on to the case of the strata in which victim's race was black. So again, we repeated the same analysis. We have the observed counts on the top, and remember, we have to compute the expected counts in order to get to the chi-square statistic. So chi-square statistic is 70.68. Again, it's larger than 3.84, therefore reject the null hypothesis and also conclude that there's an association between defendant's race and death penalty. What about odds ratios here? Compute odds ratio using the formula. The odds ratio is 4.08. How do you interpret it? So the simplest interpretation is that whites are more likely to get death penalty. But remember, you have to add that this is in a case of Black victims. And actually, I will take it one step further. I will say that when the victim is Black, the odds of getting death penalty for white defendants are about 4 times higher than the odds of getting death penalty for Black defendants. So not only these odds are higher, but they're also quantified by how much, right? And I used the actual number that we computed for odds ratio. Does this make more sense now in terms of the original question that propelled this research? Of course. So on this slide here, we have proportion of death sentences by race of suspected, of the suspect and victim, and overall cases, and we also have this stratified by different categories. So I will encourage you to look at this at home and make sure you understand how these results are obtained from the chi-square analysis. And I also wanted to mention something else. This is an example of what we call Simpson paradox. Did you guys ever heard about Simpson paradox? Simpson paradox is a phenomenon in statistics that has to do with the fact that the direction of the association that you see in a 2x2 table can be different or opposite when you include a third variable. And that's what happened. If you're interested in this phenomena, I would strongly suggest you guys just Google it. There's plenty of articles on that in the net. So ultimately, when you're analyzing the data, the goal is to include all available information and hypothesize the relationships prior to looking at the data, so your analysis is more meaningful. But I think this example showed you an importance to conducting what we call a multivariate analysis. It is very informative to look at bivariate associations, so 2 variables at a time. At the end of the day, you would like to look at more variables, especially if you're looking at observational data. Okay, and then let's just look briefly at potential alternative explanations for higher odds of white suspect given death penalty. And this has to do, or one of those points is close to what one of you were describing before. So let's look at that. Race of the victim is more strongly associated with death penalty verdict. That's obvious. Second, we also should notice that 95% of white suspects were indicted for killing whites. 86% of Black suspects were indicted for killing Blacks. And those suspected of killing Blacks were rarely sentenced to death. Right? So this is again sort of saying, when you have an interesting question, try to gather evidence and then look at this evidence from many different angles so you can get the whole story. But maybe just one last point here. This data is observational, and therefore we cannot make causal conclusions from this data. The only thing we can talk about in here is an association. So I mentioned the Simpson paradox, but this is also an example of statistical interaction. So we can say that the association between the death penalty verdict and the defendant race was modified by the effect of the third variable, the victim's race. So effect modification, statistical interactions, those are the same things. And Pearson chi-squared does not inform us where the departure from independence are, only that they exist. So typically we are interested in answering this first big question about independence, and then we are looking at the data to interpret that correctly. Related tests. So I mentioned that the chi-square test was appropriate for independent data, right? If you had paired samples measured on some categorical outcome, for example, if you are interested in, you are doing a study with elderly, and you are interested in perhaps seeing whether some exercise regimen was helpful for them, so they had reduced the risk of falling. And you can ask the question, how many times did you fall in the last 6 months? So you can ask this question prior to starting the program, and then you can ask the same participants the same question, let's say 1 year after they completed the program. Right? So the answer will be categorical. How many times did you fall? But because you're using paired samples of the same individuals, you will have to use an appropriate test for that. In this case, the test is called McNemar's test. For small samples, as we mentioned, use the exact binomial test. And there's also something called Fisher's exact test, which is used for small samples. And this test assumes the marginal totals are fixed by design. So it is applicable to certain situations. And it has been, it has a nice story behind that. So a lady was given 10 cups of tea. Well, the lady was claiming that she can tell whether milk was poured into tea first versus vice versa. And I think there was a statistician in the group at the party, and that statistician said, well, let's test the hypothesis. Let's say whether you are guessing or whether you really know. So she was given 10 cups of tea. In 5 of them, milk was added before the tea. In the other 5, the milk was added after the tea. So the fixed totals by design, we had 10 cups, and in the first 5, we have this order, and the other 5, we have the other order. So what happens, so what's your conclusion if she correctly identifies all 10 of them? Can that happen by chance or not? So this is, this test was developed based on the story. So let me just finish here to say that the null hypothesis in this case would be that there is no association between, or that she's simply guessing, so no association between the order and her guess, right? And alternative was that she actually could tell the difference. So in the summary, maybe before I do the summary, I would like to ask whether you have any further question. Yes?
So did you get?
You know, actually, I don't remember. I read the whole book about this, and I don't remember right now. Tony, do you know?
I'm not even sure it was a real experiment.
I think it was. I think it was the Fisher. Fisher was one of those. It was in England, obviously, right? It would be great to check. Yeah.
I'll check it out.
Mm-hmm. Any other questions? So, in summary, today's methods are used for hypothesis testing for 2 categorical variables. The null hypothesis is the hypothesis of independence, which is equivalent to saying that the proportions in 2 categories are the same. It is, those tests are inherently two-sided, so the direction of the dependence does not matter. But we only use the right tail of the chi-square distribution. So this is important to remember. And also, whenever we are testing hypotheses, we have to think about type 1 and type 2 error, right? So just a reminder, type 1 error is rejecting null hypothesis when null is true, And the alternative is, I'm sorry, the type 2 error is failing to reject null hypothesis when null hypothesis is false. So we do not want to commit neither type of error. So in other words, we have to control that both types of errors if we can. Okay. So I think this will conclude the lecture, and Tony has the answer.
Right. According to Wikipedia, that unimpeachable source, Moon was Muriel Bristol, and it was 8 cups of tea, not 10.
Oh,
Yeah,
interesting.
And she got all 8 right.
She got all right. Okay.
And the odds of that are 1 in 70.
Okay, great. Thank you.
You know.
Yeah.
Well,
So
like,
it's
it's like alligators in the New York City subway system. If this is what took place when, you know, long ago enough that who would be able to really ever check?
19th century, I think.
Yeah.
Yeah. Okay, guys.